That is quite a title. Thank you very much.
First, thanks for the organizers for inviting me. And I have to say, I'm kind of a last-minute substitute. So some time ago, I got a call from Rafael that, well, a speaker canceled. Would you like to come? Then I decided, well, this would give me an opportunity to get away with something that's a little bit half-baked or half-cooked, depending on your taste. And it's a stab at an open problem in the accuracy-based epistemological framework. So I will tell you in a minute. So this is a work in progress on an open problem. And by the way, I'm not fond of the word fragmentary here. I will tell you in a second exactly what I mean by that. But the thing is that the title would be even longer if I used the proper description of the things of the situations I want to discuss. So hopefully this will become clear in a second. So what I will do is, well, I will rehearse first some of the notions behind the accuracy centered approach, and of course I will repeat some of the notions, some of the things that Richard just said, I think, but you know, these are good ideas, so it will bring you no harm to listen to them twice, right? And then I will tell you about the problem, and informally, or more or less formally than eventually, the problem is this: you have two propositions, A and B, and they have a non-empty intersection, and you know what your new credence in A should be, and you know what your new credence in B should be. And the question is, how exactly should you update your belief function? For example, how should you modify your belief in the conjunction, given just the information about your new credence in A and your new credence in B? And the problem was stated by Hannes Leitgeb and Richard in their two-part 2010 paper. And well, it will take some time to set up the geometrical framework in which the problem is stated, and in which I think I solved a version of it. So yeah, this is the problem in a nutshell. So I will show a solution to it in the simplest non-trivial case, which I think is interesting. And I will show that the solution is not transferable to different cases, but I will also tell you something about the different cases. And from this, I will produce some examples of cases which I think are a bit unfortunate if you think that the accuracy-based framework should use quadratic scoring rules. And when thinking about how to update your belief function, you should minimize global expected inaccuracy, which is something that Hannes Leitgeb and Richard argue for in their paper, and which I will try to properly define in a second. All right, so first, all right, if you had a yes-no notion of belief, then something like that, the norm of truth would be the norm to conform to in epistemology, right? You should fully believe in truths. You should not believe at all, which is just you should not believe falsehoods. And, well, you should hold a system of full beliefs that strikes the best attainable balance between these, the mentioned good and evil, right? But if you subscribe to the notion that beliefs come in degrees, then this is not the most appropriate norm to formulate. And you think you might care about being closer to truth, for example. belief that's closer to truth, a stronger belief in a true sentence, in a true proposition, is better than a weaker belief in that proposition. And the main intuition behind the notion of inaccuracy, that's the key notion to this approach, is that inaccuracy is distance from truth. And as you already know, there are various ways of fleshing out fleshing this concept out. And well, the norm of truth, to again quote Joyce, becomes the norm of gradational accuracy. A rational agent must evaluate personal belief on the basis of the gradational accuracy. She must strive to hold a system of partial beliefs that, this is why I quote this thing, because this is very important, in her best judgment is likely to have an overall level of gradational accuracy at least as high as that of any alternative system. So, if that agent is not aware of some good alternatives, right, then she may be seen as not breaking this norm, I think. Anyway, the thing is, I think this formulation of norm motivates some of the definitions eventually used in this framework, like expected inaccuracy. We will be judging inaccuracies of some credence function as expected by our current functions, and I will get to that. So suppose we want to measure inaccuracy in some way, and we're thinking about a single proposition, and the way to go is to use a certain scoring rule, which can be also thought of as a punishment rule, namely, the lower your score, the better. So what the scoring rule does is it takes a truth value and it takes a credence, and it gives you a real number. And intuitively, it means, okay, if the proposition is, for example, true, and you believe it to the degree x, then your punishment is such and such. Okay? So the score of S0x is the penalty for having credence x in a false proposition, and S1x is the penalty for having x in a true proposition. Now, what we'll be interested in are so-called proper scoring rules. And these are the rules which minimize this expression at p equals x. What does it mean? Right? Suppose you fix a proposition and you really have credence p in that proposition and credence 1 minus p in that proposition. Then this expression gives you the penalty that having credence x is expected to have by your own credence. So if this is minimized at p equals x, it means that at this moment you're not thinking that a certain different credence function is better than yours. Okay, so the scoring rules that have this feature have been called by Gibbard will call immodest, but the usual definition is the usual name is proper scoring rule. So what are proper scoring rules? And I will refer to two types of them, and just know that there are at least two types of proper scoring rules widely used in the literature, namely the quadratic scoring rule that Richard was using, which is just take the square of the difference between the truth value and your credence, and a logarithmic scoring rules. These are just two examples. And by the way, if you thought a good idea would be just to take the difference between a truth value and your credence, then this will not be good. You will think that most likely you will think that a more extreme credence than yours will pay off. So now, Hannes Leikert and Richard argue at length in their paper that in context of epistemology you should use quadratic scoring rules, and for the time being I will subscribe to that. And we should use, anyway, the idea is that we should use a scoring rule to measure the inaccuracy of a credence function. Let's define this properly. So suppose we have a finite set of propositions. Possible worlds relative to that set are just classical valuations, and a convenient tool is the omniscient credence function, right? So the omniscient credence function in world W is the one that just assigns 1 to truths and assigns 0 to falsities. And the main idea is that the inaccuracy of a credence function in a world is its distance from the omniscient credence function. So how far are your beliefs from the best beliefs? Right? And now, what the exact notion of distance will be, and if it even may be properly called a distance, it will follow from which proper scoring rule you will use. So in general, if you have a scoring rule S, then you just go through all your propositions, and to have your the inaccuracy of credence C at world W, you just sum the penalties for having a credence C given by C in a certain proposition, depending on the truth value of that proposition in the given world. And if you use the quadratic scoring rule, then what you end up with is really the squared Euclidean distance between the omniscient credence function and your current and your given credence function thought of as vectors. So, as you now well know, the notion of inaccuracy has been used by Joyce and by Richard and by some other people to justify various epistemic norms, including probabilism. And to talk about this, we need to have more structure in the framework. So this is a general definition of inaccuracy, which I think is can give you also a general view of what the functions are supposed to be. But we really want to have an algebra of propositions. Okay? So now we will. I will introduce the bits of the geometrical framework from Hannes's and Richard's paper that they used to formulate a problem. And, again, we have a finite set of epistemically possible worlds, or an agent. Propositions are just subsets of this set. And each world is just a unit vector in R times the cardinality of the set of the possible worlds. So now each possible world is just a vector with a single one somewhere, right? And zeros. Now, a credence or a belief function is just a function that gives you a positive real number for any proposition. But now, a useful notion is that of a global belief function. This is a function defined on the set of worlds itself. So it gives you a number for each separate world. It summarizes the agent's attitude to each of the epistemically possible worlds in his set of epistemically possible worlds. And of course, when you have a belief function, then you automatically have a global belief function, because if you have a belief function, you have all the beliefs in single points. And of course, this gives you a global belief function. But to go the other way around, well, we need to assume probabilism, and we do, right? In this talk, we do this. So, so now, to measure inaccuracy of a credence in a world, we can use something called global inaccuracy measure. So, you remember that a world is a vector now with a single one and lots of zeros, right? And a credence and a global belief function is also a vector of the same length, right? And so to judge the inaccuracy of a credence B in the world W, we will just take, assuming you're using quadratic scoring rules, this is justified, we will just take the square Euclidean distance between the world W, which is a vector, and the set of values of the global belief function determined by B, which is also a vector of the same length. So this is nice geometrically, right? Because you can think of this of inaccuracies as square Euclidean distances. And all right, so now we can we are close to formulating the problem. So some things about how you should update your credences. Well, the most well-known case is in which in which the evidence you get entails that a certain proposition, this, should receive credence 1. What should you do? Well, just forget about this thing, right? This will give credence 0 to everything inside that. And if you had a proposition that overlaps this 2BL in general, if you have any proposition, your new credence in that proposition should be the conditional credence of that proposition given. Right? Well, yeah, this is sometimes called full conditionalization. And, well, what it can't do, for example, is it will never raise your credence from 0. Right? Where some people may have intuitions that this is exactly how it should be, right? But I'll just put that on the table. All right, there are some very well-known arguments, let's say pragmatic arguments for conditionalization. I will not rehearse. Now, what happens if instead of getting evidence which entails that your new credence in some E should be 1, what you get is the set of your new credences in a partition of the set of your epistemically possible worlds. Then, well, the generalization of the full conditionalization approach is so-called Jeffrey conditionalization, which says, well, scale in the most intuitive way. So if you want to arrive at your new credence in A, well, take the conditional probability of A given E1, right, times your new belief, your new degree of belief in E1, and sum that with all the other similarly calculated bits. So this has some nice features, like, for example, the full conditionalization is a special case of that. well, some people object that Jeffrey conditionalization has a weird feature that it's order dependent, and if you get the same evidence, same bits of evidence in different order, you might arrive at a different belief function. But this is debatable. I mean, there is a certain mathematical fact that is that is certainly true, and but the philosophical interpretation of that is debatable. All right, so we have two quite intuitive update functions, and can we argue for them in an inaccuracy-based framework? And Hannes and Richard show we can, and the way to do it is to show that using the update rules, using an update rule in a certain situation minimizes global expected inaccuracy. So, in general, suppose you have credence B at time t, and between t and t prime you get new evidence. What this new evidence can entail is, for example, numerical constraints on your new credence function, right? But what it can also do is just show that you should exclude some worlds from your set of epistemically possible worlds. And I'm mentioning this because I guess there are many people in this room who enjoy non-monotonic logics and who will most likely try to tinker with this. And I'll be very interested to see how this can be, how this definition could be changed to fit some non-monotonic cases. But anyway, this restriction will not happen in the cases I will talk about, but I wanted to give you a general definition. Suppose your current credence function is B, right? And your evidence restricts your possible worlds to the set E. How to calculate the expected global inaccuracy of a new credence function B prime? Well, what you should do is to go through all the possible worlds that will be possible, right, at T prime, and just multiply your current belief in that the given world is actual times the global inaccuracy of B prime in that world. All right, so finally, I hope some interesting bits. For example, Hannes and Richard show that full conditionalization does minimize global expected inaccuracy. Again, we assume the quadratic scoring rules are used. But Jeffrey conditionalization does not. And they devise a certain rule called alternative Jeffrey conditionalization, which does minimize global expected inaccuracy, which has the feature that's welcome for me, for example, that it allows you to change your credence from 0 to something else. And but it has a different feature, namely when you calculate your new credence in a proposition, at a certain point you need to divide what you're calculating by the number of possible worlds inside that proposition. So what you're doing depends on the cardinality of the propositions, and I will get back to this. So now we can tackle the problem, right? Assume we're using the quadratic scoring rule. Suppose A and B are two propositions with a non-empty intersection. The evidence you receive entails and entails only that your new credence in A should be P and your new credence in B should be Q. How should you update your credence function? And in this context, the question is, what is the rule which minimizes global expected inaccuracy? So, if you think how to approach the problem in a simple case, so if you think, for example, of the following case, you have 4 possible worlds. This is A, right? This is B, right? What you know your new credence in A, this is P, right? Right. And your new credence in Q, in B, which is Q. Right? So in this case, what matters, I mean, one way of solving this is to calculate your credence in A and B. Right? When you have that, you can calculate everything else. Right? Because P and Q are given. So given that, you have P minus that is this, Q minus that is this, and 1 minus all of that is this. So the solution here really boils down to calculating the value of your new credence in the conjunction. And I have to say that something not prima facie absurd is going on. So if you look at the expression that's conveniently rendered in smaller font here, what happens is that, barring some exceptional cases, maybe more of that in a minute, the change of your belief in the intersection is the average of the changes of your belief in A and the changes of your belief in B. So, for example, if you're told to keep your belief in B constant, and you should increase your belief in A by 0.2, then you will have to increase your belief in the conjunction by 0.1. I think this is at least not absurd at first sight. This is how it works in that case. And of course, how to reach this? Well, what you need to do is, once you know that everything can be formulated referring only to the value of your new credence in the intersection, then you just need to minimize a function of one variable that contains lots of squared things inside, right? So this reduces to some tedious but doable calculations, right? And if you do it this way, then you should, of course, see immediately that adding new worlds increases the amount of work you need to do immensely. So yeah, I'll get to that soon. So at this point, I think what we see is quite well, not immediately absurd. I would even say quite a natural way of thinking how to update, how to arrive at your new credence in the intersection, in the conjunction of two events, from the information that we're given. And at this point, you could have, and I certainly had, an idea of how to solve the problem in general. As I told you, there is the alternative Jeffrey conditionalization rule, which we know from the result of Matt and Richard, to minimize global expected inaccuracy, which means we know that it works. So you could think that in general, if this is the sphere of your epistemically possible world, right, what you could do, given proposition A and proposition B, you could first abstract from all the worlds inside, right, and distill from it the 4-element structure, right? A and not B, A and B, B and not A, not A and not B. Because, well, why should the level of, how much the sphere of my epistemically possible worlds is fine-grained influence the outcome of this, right? So what you could do is to distill the 4-element structure from that, get the credences in these 4 elements from your structure, calculate the result using this simple rule, and then what you have is the information about the partition, a 4-element partition of the space. So you could use the alternative Jeffrey conditionalizations to get that. And it turns out, no, you can't do that. Turns out if you want to minimize global expected inaccuracy and use quadratic scoring rules, then for example, your new credence in A and B will depend on how many events there are inside A and inside B. And of course you could say, well, we already knew that the alternative Jeffrey conditionalization method depended on the cardinality. But what I was trying to do is to have a procedure whose output would be the input of the alternative Jeffrey on the conditionalization. And what I showed is that you can't think of that the simple procedure outlined here will not work in general. So let me illustrate what I mean. So I will use some examples modified from examples by Osherson, who has a very nice paper about Jeffrey conditionalization. So suppose, listening to the radio, I hear a forecast for rain, but I'm not sure whether it comes from the chief meteorologist or from his deputy. So I believe both of them to be equally reliable. So at the moment, I have this credence function, where R is it will rain today, and C is the chief was speaking. So I set this up so that C would conform to A and R would conform to B. So suppose that I get two information about my new credence. So I glance at the sky and I think, well, I'm kind of now more convinced that it will rain. So a glance at the sky raises my credence to 0.7, but when they rebroadcast the forecast, that it gives me evidence that I should keep my old belief in that the chief was speaking. Okay? So what happens is I have difference 0 in my belief in C and a difference 0.2 in my belief in R. So it works as it should. I need to increase the belief in the conjunction by 0.1, and this is exactly what we get. I think this doesn't strike one as immediately absurd, and anyway, it follows from the theorem. So now there will be at least 2 problems with that. One will just show you that this simple rule, that the answer to the problem really depends on cardinality, and that the simple rule I showed you will not work in general. And the second related problem is that even if we stop at 4 worlds, we can produce cases in which the way the agent is supposed to update her credences is really unfortunate if we use quadratic scoring rules, I think. So let's start with the second problem. Let's give this event one more possible world. Okay? Let's see what happens. And the story goes like that. So we modify the meteorologist's story. So suppose I owe the guy money, and I don't want to meet him. Okay? Every day, I walk my dog in a certain park, and my priority is not to disturb her routine. So I always go to the park. The thing is, the chief meteorologist is at work if and only if it's him who was talking during the broadcast. So I know that whenever it does rain, he comes home using a bus. And whenever it doesn't rain, he goes to the exact park that I go to, and then uses one of 2 possible routes. Okay, 1 or 2. And the proposition B will be the chief meteorologist will walk via path 1 today. So, as you can see, if it rains, then it follows that B is false. If the chief's not there, it also follows that B is false, because he doesn't enter the park at any other time than coming home from work on a sunny day. So the only world in which something happens is the one we have to split is the one in which it doesn't rain and he's at work. Okay, so now we have two possible worlds in which he goes via path 1 or he goes via path 2. And now, if you remember, I had the credence point 2 in C and not R. So let's split it to point 1 and point 1. And this doesn't matter at all right? We just need to choose two numbers which sum to point 2. And the way we will be supposed to change the credences will be exactly the same. But suppose we do that. And we're faced with exactly the same evidence. So we glance at the sky, and we raise our credence in rain to 0.7. But we conclude we should, after hearing the new broadcast, we should keep our credences in C. And if you painstakingly calculate what your new credence should be, so you minimize a function of two variables, then you will see that, for example, when it comes to the conjunction of R and C, which is this, the beliefs will be different. So, to sum up this example, we have two agents. So now, of course, you will tell me that R is not the same proposition for the two agents because it has two worlds in one case and three worlds in a different case. That's right. But the thing is, both agents can be described using this description, and then the place of R can be filled in two different ways. So they have the same, they start with the same credences in R, C, and the conjunction. They face the same evidence, right, which implies that they should increase the credence in R in exactly the same way, and they should keep their credence in C. They ended up with a different credence in the conjunction, and it would seem the only difference was the level of fine graining that's involved, namely whether the part was considered or not. So now what you have is a mathematical fact that the simple rule that I showed you does not work in more than 4 worlds, at least not in general. Okay? But now you could be worried whether this sort of updating is really the way to go. I think some people might be a bit uncomfortable with how these two agents update their credences. But if we continue on that topic and come back to the 4-world case, we can illustrate by ways of very, very simple examples some, again, unfortunate situations if you update your beliefs when you want to minimize global expected inaccuracy using a quadratic scoring rule. Okay, suppose again I start with the same credence. But now what happens, I get in a way symmetric, or if you prefer anti-symmetric anyway, evidence. Namely that I should increase my credence in R by the same factor by which I should decrease, it's the other way around. I should lower my credence in R by 0.1, but I should increase my credence in C by 0.1. So of course, from the theorem, right, it follows that I minus 1 plus 1 is 0, divided by 2 is 0. So your belief in the conjunction should stay the same. But you need to lower your credence in R by 0.1. Well, so what you have to do is to lower your credence in R and not C by 0.1 to 0. This is the lowest possible credence, and it's I think it's, well, at least not evident that this is the way to go. That faced with this evidence, you should end up with credence 0 in R and not C. And what happens is that, well, what I did, if I updated my credences in this way, I treated R and C as if they were perfectly anti-correlated. So as if I just didn't see the RC option. So when I see that I should lower my credence in R, that I'm somehow blind to this, right? The only option I see is R and not C. So this is what I should decrease. This is what I should lower. This is what the inaccuracy, minimizing global expected inaccuracy tells me to do when I'm using quadratic scoring rules. And by the way, if I'm supposed to increase both of credences in R and C by the same amount, then it happens that I should only increase my credence in the conjunction. Again, this follows from the theorem. Of course, there will be various cases in which something is 0 or more than 1. This is easily accommodated for. But this is the general behavior. So first, it's general or on a few levels. So when you think about the forward case, this is what always happens. If you have the same increase in credences in two propositions, which are related to each other in this way, you should increase your credence in the intersection. And if you should lower one credence and increase the other credence by the same number, then you keep this constant and you change your credence in these two. So yeah, I think this might be seen as a bit unfortunate. And well, I calculated that the case with the additional world here, and it also goes through. This behavior is also present in the 5-world case. So the last bit that I want to talk about involves the interpretation of conditionalization. So if you take, that's a quote from a very interesting paper by Van Levenstein, about which I will say one thing. That situations that call for full conditionalization involve ruling out worlds from the set of epistemic possibilities. And now I would just like to bring attention to the fact, sorry if it's trivial, but I think it's interesting to notice that the options of deleting a world from the set of your epistemic possibilities and leaving it in, but assigning credence 0 to it, these are really different options. And what I mean by different, so if you take, for example, if you take 5 possible worlds, and you have agent 1 who doesn't see this world, his knowledge excludes that, and he has credences like that, okay? And if you consider a different agent, for whom this world is inside the sphere of epistemically possible worlds, but he gives it the singleton of it credence 0, and it goes like that. Okay, so the credences, if we forget about that, are exactly the same. And if we give these two agents, exactly the same information about their new credences in these two propositions, they will update in a different way. Okay? So, and I now realize that the same point could have been made just using the alternative Jeffrey conditionalization rule. So yeah, we don't need to consider overlapping propositions, but we may if we want. So what will happen is, faced with the same evidence, they will update in a different way. So, for example, if 5 minutes ago you were an agent like B2 who had these 5 possible worlds, epistemically possible worlds, and what you learned was that this proposition is true, well, that your new credence in that should be 1, all right? This is what you learned. This is exactly a situation which calls for full conditionalization. It will really matter whether you, if you use minimizing global expected inaccuracy. It will really matter whether you just delete this world from the set of your epistemically possible worlds, or leave it in but give it credence 0. So I think this is a bit too fast, and these are certainly, I think, issues that one should, that are interesting to think about. I'm not sure what to think about this myself. So what I did is I showed the solution to Hannes's and Richard's problem in the simplest case, and well, I think the advantage of it is that it's a formula that you can understand, right? And sometimes in these frameworks you see some bits of math that do not make for easy understanding at first sight. And well, I showed you that unfortunately this solution is not transferable to different cases. And I showed you some examples of updating required by minimizing global expected inaccuracy combined with quadratic scoring functions. So, in these cases, I think may be seen as somewhat unfortunate. So, an obvious thing to do, right, is to check whether we can fare maybe better or differently. It would be interesting if we use a different scoring rule. For example, if you use the logarithmic scoring rules. So, Levinstein showed that if you get information about the partition of your belief, of your set of epistemically possible worlds, then if you use logarithmic scoring rules, then the rule to use is Jeffrey conditionalization. This is the rule which minimizes global expected inaccuracy in that case. So this is certainly something to check what happens in this case. All right. Thank you very much.
All right, so questions from Dr. Wronski. Richard.
And so one thing is just a comment. So there's an oddity about the Levinstein results about Jeffrey conditionalization. He uses, so there's 2 versions of the logarithmic scoring rule. One only really works on probability functions, and the other one works on any-credence functions. So the one that just works on probability functions makes your score just the log of the credence you assign to the particular world that you're at. And that's kind of fine for probability functions because your other your credence functions in time are determined by the credences of those worlds. But there's another one which is more like the one that you were stating, which assigns a different, and then so a different score to each credence and then summing them up. And it turns out, funnily enough, that doesn't give you, that second one doesn't give you the general conditionalization. So it may be that something also goes wrong there. So that was one comment. And the other one was that it's funny that, and I don't know if there's any real connection here, it's just a word association. That a similar thing to this happens in Hannes Likely's recent so-called stability theory of belief, that where he tries to connect your theory of full beliefs to your theory of partial beliefs. And in that he also gets partition relativity. So an agent with those 2 probability functions that you give might end up believing a proposition relative to one probability function, but not believing it relative to another one that looks exactly the same, but where the partitions. Anyway, that was
Thanks.
good comment.
Thanks.
Dietrich?
Well, thank you, Leszek. That was very nice. But I have a little problem with what is the general aim of these considerations. I missed at the beginning. I'm sorry, I didn't find an abstract, but I understood the previous lecture as argumentation about the acceptance of certain principles. So how can you justify to accept certain principles with respect to probabilities? But of course, you cannot use these kind of considerations, for example, to understand fragments of the history of the sciences, because there you will have conceptual shifts, and it simply doesn't make sense anymore to speak of, to compare them, that they are, as it were, in different logical spaces. So, would you consider, well, no, let me put it as simple as possible. What is the general aim of what you were doing? Is it like contributing to the program of Richard? And is the fact that there are sometimes conceptual changes, does that influence at all these kind of arguments?
So about the second bit, I don't know. I think these things are difficult enough if we keep as many things constant in the background as we can. Okay, and I'm really not sure how to extend. I mean, the examples one usually thinks of are agents who, from like 1 second to another, right? They receive some evidence. This is usually thought of something on a different scale than a conceptual change. So I'm not sure. Maybe there is some kind of applicability of these results to something like that. But yeah, I thought whether you could think of results like this, apply them to funding, to dividing funding of a faculty, but I have to work more on that. So there might be some applications to different things, but I'm not sure. But as regards to the first question, yes, well, my aim was just to contribute to that project, that there are some epistemic norms. First, you can think of some epistemic norms, which you might find plausible, and think whether they're justified from an accuracy-based framework or not. But then there are situations in which you might not be sure what is the norm that you should apply. Right? So, for example, well, you receive a certain type of evidence. What is the way to go if we subscribe to the accuracy-based framework, which I think has a lot to say for it epistemologically. So the thing is, this problem is just, well, discover the norm mandated by this framework. So that's it.
Katie?
Yeah, thanks. So it seemed interesting to me this your worries about invariance to fine graining, and I do find it plausible that you might want to stipulate as a constraint on these accuracy arguments for updating that if they're going to say anything sensible about certain situations, I mean, maybe there's nothing sensible to say about this case that you're interested in. What should we update A and B to, given that we have a glimmer of what we should update A to and B to separately? I mean, maybe there's just nothing sensible to say, but if there is something sensible to say by these accuracy arguments, I'm with you that, there's a worry. I mean, maybe certain types of invariance conditions are important, right? But I'm just wondering, I mean, maybe you were doing this with your examples. Can you think of any good reasons why invariance would not be important to fine grain in your particular case? Like, is there any kind of intuitive argument why, the number of fine grain propositions does matter?
Well, I don't have a good argument, right? So the examples I considered were like this. This was the initial example, a forward case. Then I considered this, and then I did, which is something that normal people should not do, but in quest for truth, you make sacrifices. I calculated this, so when you minimize function with 3 variables, and well, what I found is that all right. Suppose what you're doing. So I'm sorry, this will take a minute, but I think it's a very interesting. It's a very interesting question. The idea in all cases was keep. So this is B, right? Keep B the same, and increase this by the same number. Okay. So let's call it N. So in this case, what you did, well, let's take half of N here and the other half here. In this case, no matter what the numbers actually are, you get 3/7 of N here and 2/7 here, all right? And in this case, if I didn't let's say they didn't make a mistake, then what you have is 4 out of 10 and something like this. So the thing is, you can see this is always, the change is always the same outside the conjunction, which is something you would expect from something like the alternative Jeffrey conditionalization, right? But this decreases the change in the like 3 out of 7 is more than 4 out of 10, right?
Yeah.
Yeah. So this decreases. So it would illustrate something like that. That if you can think of more ways, right? The more ways you can think of in which A and not B can realize, in comparison to how many ways you can think of in which the conjunction could realize, the less the weight, the bearing of your increase in the conjunction of A in A has on the increase of the conjunction. Okay, so it's kind of, if you can, it's completely non-probabilistic, right? It's like if you can think of more ways in which something can happen, right? If your knowledge doesn't exclude that, maybe you have credence 0 in it. Okay? Then somehow more of the mandated increase in your credence needs to go there. Okay, I'm not sure if that's a good feature or not, but it works like that. So I don't have anything more to add to that.
Just a quick comment though. You have added further structure in that example because you're stipulating that only one world is A and B, and you're expanding the cases.
Yes. You're
so
right.
that's a bit different from just, I think, straight out partition
Yeah, but on that I don't have anything to say.
Yeah, sure. Okay,
Yeah.
but in terms of cashing out the intuition,
Yeah.
we can do it for this special case.
Yeah.
I see what you mean. Okay, thanks.
Say yes.
Okay, so the way you set it up, you have a private credence over this space, and then you have a scoring rule, which is proper. So that means we automatically also have an asymmetric distance measure on the space, in that you can measure excess penalty. So I can measure the distance from my belief to some other reported function by seeing how much more I have to pay if I report that false belief. Then you're saying, what happens if we place some hard constraints on your reporting? For instance, whatever distribution you report, it has to assign probability 0.7 to this particular set. Or maybe there are more constraints. Maybe this set has to have. Okay, so that's a well-defined mathematical problem. It's a variational inference problem, in fact. So why not just solve that?
The thing is that what's most probable is that I don't grasp the full mathematical intricacy of this, right? But what I see is that the form, the nature of the equations you need to consider really differs depending on what the cardinalities of the propositions are. So I don't have a general formula. Okay, here's a function, let's minimize it. Okay, and what you need to do really changes depending on the events. So I will be very glad to talk about it, because the most probable thing is that you tell me which field of mathematics I should study more. But if I do it the bottom-up way, let's really think what the function is that we should minimize. Then what happens is that the function itself really changes depending on the case. So I don't have a general method, a general description of the form of the function.
But often in variational inference, what people often do is to do calculus. Like they use Lagrange multipliers and use that to. Something you often do is to say in truth, these gazillion different variables are probably not independent, but I'm going to approximate them by a distribution where I force them to be independent. And I then want to minimize the excess penalty by choosing the wrong distribution, which is closest to the true distribution with these constraints. This is often, well, actually it's often not terribly difficult mathematics, because you only need to be able to do differentiation, especially if you have a small set of, like in this case, of finite. But I mean, this is often like a top-down as opposed to starting out saying, is there perhaps a really simple formula that would express the answer? And as you point out, there isn't.
Okay, thanks.
Is there anyone that has a very quick question? No, that's right. So let's thank our speaker again.